Okay, thank you. So Dolores Knipe received her bachelor's degree in agriculture at the University of Missouri in 1976, and then her master's degree in atmospheric science at the University of Missouri in 1984, and her MS and PhD in atmospheric science in 1988 and 1989, respectively, at UCLA. Now, during a lot of this time, she was an officer in the Air Force. So Dolores was an officer in the Air Force between 1977 and 2008. And during the early years, she had several assignments related to space science and meteorology, but most of the time, she was a faculty member at the Air Force Academy in the physics department. And in fact, in 2008, she retired as, I'm guessing, Dolores, Lieutenant Colonel, and professor of physics at the Air Force Academy. And for the next 4 years after she retired, she didn't really retire. She had some various positions at NCAR, NOAA, and the University of Colorado. And most recently, in 2013, she became a research professor in the Department of Aerospace Engineering Sciences at the University of Colorado, and where she still holds that position. And in 2014, she became editor-in-chief of Space Weather Journal. So Dolores is not a very good example of, if you want to go on retirement, you know. So the nomination for Prize Lecture recognizes the recent distinguished work led by Dolores that unravels the physical connection between shock-led interplanetary coronal mass ejections and the relatively muted neutral thermosphere density responses that follow them. She, her group, and other colleagues discovered and demonstrated that the weak density responses are due to the enhanced nitric oxide production and associated NO cooling that result from the elevated particle precipitation prompted by these particular solar wind structures. Through the above work, Dolores has enlightened our knowledge of a complex chain of events coupling together the solar wind, magnetosphere, and thermosphere. This relationship between elements of the solar terrestrial chain is at the heart of CEDAR Strategic Thrust Number 1, encourage and undertake a systems perspective to geospace. So with that, I'd like to welcome Dolores and congratulate her on the CEDAR Prize Lecture this year.
Thank you. I am very honored. I can't tell you how surprised I was when I got the email of this announcement. I have to tell you, I almost fell over. It was one of those things where you think, oh, you're just doing the routine work that, you know, build up over 30 years, and that is exactly what has happened. 30 years ago, I showed up in Barbara Emery's office and Art Richmond's office as a somewhat older, because I was in the Air Force, but very green graduate student. And with the help of Barbara, I survived the 3 years that the Air Force gave me for a PhD study effort at UCLA, and it laid the foundation for the kinds of things that I'm going to talk about here and the kinds of things that I am so passionate about in working with my students, many of whom are listed in this byline. All of these are students or former students, and now Tomoko Matsuo has joined our team in the SMED Aerospace Engineering Sciences Department, and she has a very strong role in some of the work that I will be describing at the very end. I would also like to note that this work is sponsored by NSF, NASA, and AFOSR. You can't put this kind of system science work together under just one grant. It takes a lot of effort and just thinking about things. So with that, I would also like to thank Sabani for introducing the idea of these large-scale coherent structures. I'm going to be introducing the idea a little bit later on of something called a planar magnetic structure, which is a structure within another structure in the solar wind. And they are the structures that develop in the shocks that come ahead of the very fast CMEs, and we believe that they are at the root of producing this amazing chemical called nitric oxide and helping the atmosphere keep a lid on when storm heating gets very intense. So without further ado, I've shown you what is probably one of my favorite pictures. We're down here. Here's the troposphere, the stratosphere, into the mesosphere, and then into black. Nothing there, right? Except that we know the space isn't really a vacuum. It's better vacuum than we can create here on Earth, but it does contain a number of chemicals and constituents that everyone in this room has to think about at some point in time. And one of them that I think about is nitric oxide, although I only started thinking about it about 12 years ago. So you're going, what we'll do is just a brief motivation. Probably half of the time I'm going to be talking today about the motivation and some historical aspects of this and a brief overview. And then the remaining half of the time I'll talk about the storm time behavior and solar wind influence. And just so that you know you're getting more than you paid for, there will be a little bit more at the end where I want to advertise some results from students who are making their presentations here. I will also point out to you that most of the data that I'll be talking about comes from the timed SABRE instrument, which is an instrument designed to look into that black region of space and actually see the infrared emissions that tell us that nitric oxide is active. The paper that this comes from is open access in Space Weather. Who'd think I'd publish there? Feel free to dig in and have a look. So for the first 25 years of my research experience, I was much more engaged in how much energy came into the upper atmosphere. I really wasn't too concerned about how you got rid of it. I just wanted to know how it got in. This is an update of some work that I did in 2004 with undergraduates at the Air Force Academy, where we simply tried to get a handle in a very coarse way on how much energy is coming in via three paths. So there is the solar power, the extreme ultraviolet, joule power, which is coming in via dissipation of currents, and what is called hemispheric power, but you would actually recognize as particle precipitation power. And the color codes here indicate that in general, the sun produces most of the energy input to the upper atmosphere, certainly on the day side. And then the joule power, the dissipation of geomagnetic storm energy, is primarily associated with essentially the dissipation of energy via currents, and it looks like the particle power doesn't play much of a role. Well, actually it does, and it plays a huge role in the cooling. So here it comes. And you can, by the way, you can see the solar cycles here. October of 03 actually probably was close to what came in March of 1989, but it occurred over 2 days, and these data are one-day average, so it doesn't quite look like that, but it was a big deal. Okay, so from Marty Malenzek, who is inspiring much of this work, but not quite here yet, let me focus on, or point out to you that here's that solar wind EUV energy input coming in. Doesn't say much about solar wind, so that would be energy dissipated via currents and particles. Then heating that goes on from above, there's a thermal gradient, so there's heat conduction, there's energy coming down, and I didn't even mention the tides and waves that are coming up from below. This region right in here is probably the place where everyone in this room can agree that coupling energetics and dynamics of atmospheric regions, really the rubber meets the road in that area. And so it's this place where there is a lot of heating going on, and the question that you have to ask is, well, how do we get rid of this? Otherwise you get this atmosphere that just blows up. It doesn't do that, clearly. So what's keeping the lid on? And a lot of that keeping the lid on business has to do with long-term cooling from the villainous CO2 molecule, at least villainous down in our parts of the world where we live, but it is the primary cooler for the upper atmosphere. But it can be absolutely overwhelmed during storm time, and there is then a need for some additional cooling agent. In this case, it's nitric oxide. I have a little diagram of nitric oxide here. Clearly, these molecules are too small for us to see. They're separated, these two, the nitrogen and the oxygen, by about 112 picometers. So you can get a good size. These are really tiny molecules, but this is a mighty molecule. It's the molecule that can and does. Interestingly enough, if you do a Google search or anything else, Wikipedia, what you will find about nitric oxide was it has been designated by the AAAS as Molecule of the Year in 1992. Amazing. It was part and parcel of a Nobel Prize awarded in 1998. And all of that has nothing to do with this. It has to do with the fact that nitric oxide is a biosignaler. It is something that our bodies absolutely require to control smooth muscles. It is also quite toxic if made. It is a pollutant in the lower parts of the atmosphere where combustion and smoking will essentially create it and allow it to then interact. It's a very interactive molecule with other materials and form things like smog. So it has this incredible reputation, and none of that is well documented on any site. You actually have to go into our literature to find out about that. So it is, amongst many things, and I'm going to spiral kind of back and forth between time and space and history and present. It is a trace atmospheric constituent. Its mixing ratio at most allows it to be 1/100% of the constituents in the upper atmosphere. And so you think, how could a molecule at that mixing ratio have this much influence? More to come on that. It is sourced in a number of energetic environments. There's lots of ways to make it. Solar protons and galactic cosmic rays precipitating into the mesosphere have a role in producing nitric oxide. You need very energetic particles because you need to break the bond between molecular nitrogen in order to get that single nitrogen that will marry up with an oxygen. And molecular bonds of nitrogen, molecular bonds of nitrogen are very strong, so you need some way to break that up. It can be created by solar X-rays and EUV photons in the lower ionosphere. Again, very energetic interactions on a particle-by-particle basis. And then it can be created by photo and auroral electrons and possibly protons precipitating into the thermosphere. So back to that idea that it was kind of a small amount of energy coming in from those particles, but they have a nonlinear role as well. What I have here is the mixing ratio that was estimated by Charlie Barth, who is kind of at UC Boulder, last king of nitric oxide. He spent a very large part of his career researching it. And these data were either taken or modeled as a result of a mission for atmospheric spectroscopy that he ran on the space shuttle in 1985. There's a very long history to this molecule and its behavior. This molecule shows very high and variable density in emissions, sometimes by factor of 10 over 27-day and 11-year variations, and sometimes over that same kind of thing over extreme storm variations. It is also a material or a constituent that we tend to find, most of the time, located at highest density in the auroral zones, but it refuses to stay there. One obligatory chemistry slide, all of this is being captured, so you can go back and take a look at it. But what I want to point out to you for the purposes here is nitric molecular nitrogen in the thermosphere is going to interact with something energetic, in this case, an energetic electron that could be either from an auroral event or from a photoelectron event, and it's going to break up into excited nitrogen and ground state nitrogen, or maybe some combination thereof. But it's this excited nitrogen in its 2D state that has an affinity for molecular oxygen and then breaks up into nitric oxide and another oxygen with which it could potentially interact later. It is also, there are other ways of making nitric oxide. We can have an ionized nitrogen molecule interacting with oxygen, and here comes this needed excited nitrogen atom again. And now we get something for nothing. We get an NO plus that, if it's neutralized, gives us a nitric oxide molecule. And then, even more interesting, that can sort of further react and give us another excited nitrogen. So you might suspect that this is a nonlinear process, and it is. If you've ever had a look at Justin Yonker's PhD dissertation, he has these diagrams with nitric oxide going in all directions, and it almost makes you dizzy. And that's only for one chain of the interaction. So I will just leave you to contemplate the idea that there's a lot of interactions going on, and furthermore, we've got this nice friendly ground state molecule. It can interact with a very temperature sensitive reaction with molecular nitrogen or oxygen and create another NO. And so both of these atomic nitrogens actually can get into the act to make this molecule. There are loss mechanisms, and interestingly enough, it has to do with having the amount of stuff that you've made come back and interact with it, and then recreate the N2 that you can reprocess some more. Highly nonlinear interactions. The bottom line is both of these molecules, atoms, are sources of nitric oxide. And you can read more about that in Charlie Barth's articles in 1995 and 2003. So the general view that you should have of this is, and I will do a bit more, at high latitudes, NO is created by precipitation of energetic particles. At low latitudes, it's created by solar-produced photoelectrons. And in the middle is this storm time gray area where we transport this chemical. And so during extreme storms, you can actually have sort of the whole globe radiating in the infrared. So I've probably mentioned many of these things. What it does is, if it gets into the ozone, it can act in a catalytic sense to destroy some ozone in the stratosphere. It was actually first investigated for its role in forming the ionosphere-The region and the implications that it had for radio propagation. It exerts incredible control in the lower thermosphere in terms of essentially generating a thermostat effect, which I will discuss here very briefly. So it is a part of CEDAR's domain. To give you a sense of what the effect might be, there's no nitric oxide on here, but here is it's a 7-day record of what the density looked like from the CHAMP satellite extrapolated to 400 kilometers. The day side is in blue, the night side is in red, and you can see this density at 400 kilometers is highly variable as a result, you don't know this yet, but I will tell you, of 3 CMEs that came from the sun, just one right after the other out of the same area, homologous CMEs. And you notice that after the first one, the atmosphere kind of settles down and goes, okay, back to normal. And then the second one hits, and it settles, but it actually ends up in a more collapsed state than when it started. And you go, how could that happen? The third one hits, and the situation's even worse. This is an example of what I believe to be nitric oxide being made prodigiously by both heating and particle production and putting the atmosphere in a state where it actually overcooled as a result of this extreme infrared cooling. So how does this molecule radiate in the infrared? It's a heteronuclear linear molecule. It's not quite balanced. And what that means is it loves, when it's heated or excited, to just stretch. And when it takes in a quantum of energy, stretches out a little more, gives away a quantum of energy. If you think, well, eventually, okay, it's going to, collide with things and run out of energy. But if it collides with heated oxygen, which it will in the heated environment of a geospace storm, then it just continues to oscillate. More and more of it gets made by the processes I've already described. And essentially what it has is it has various energy levels that it can oscillate at. The fundamental is for nitric oxide, 5.3 microns, and then there are various overtones. If you keep adding in energy and hitting it, eventually it can dissociate. So there's enough energy at some point that you break it apart, and then it can go back and recycle itself. A very abridged history, and I'm only going to highlight a couple of these things. In 1945, even before what I've got on here, Marcel Nicolet, for whom the Nicolet lectures are named at AGU, started thinking that, there might be something going on with this molecule. And he actually anticipated that it was going to be emissions in the UV. And NO does emit in the UV if it's electronically excited. So he estimates from some measurements made by V2 rockets that were acquired by U.S. investigators from the German stash in World War II, that this is what he could estimate the NO density profiles in the mesosphere. It wasn't until Charlie Barth started doing rocket experiments that he discovered, it's in the thermosphere as well. Then as more and more modeling and rocket and then satellite experiments developed, we realized that it's not only the UV, but we have here the IR, and Kuckartz in 1980 first realized in the GRL article that nitric oxide actually could do some amazing things in terms of cooling the atmosphere. Ray Roble in 1998 put together the first version of what is now what we call the TIEGCM, and he included minor species because he knew that those had to be included in order to get the temperatures right. Sawaka Maeda in 1989, while I was busy doing my PhD dissertation, was working with Tim Fuller-Rao, and in her models, in Tim's model, she also noticed that during these large storms, there could be these unusual cooling situations. And so that was our first hint in terms of theory that things might go wildly out of control. I did mention to you that there are interesting distributions. These are mostly altitude, latitude distributions from various authors, but what they point out is that at low latitudes, there tends to be a solar-driven component of nitric oxide. At sublatitudes, nitric oxide is being made due to compressional heating in this temperature-sensitive kind of environment, with maybe some of the nitric oxide coming from higher latitudes and dropping into lower latitudes. And then we have our auroral zone nitric oxide component. If you look at the data that was acquired by the SNOWY experiments, we actually had a student nitric oxide experiment. It was the first Explorer, I think, was the first of this Explorer series, and it was a student experiment, and Dan Marsh eventually took the 4 years of data acquired from that satellite and started looking to see if he got the same kinds of latitudinal, altitudinal distributions, and he did. And he had enough data to actually draw kind of global patterns. So he did the first empirical orthogonal function analysis of these so that he could get kind of a global view of what this distribution looked like, which we will come back to in a moment. But the bottom line is that the density tends to be larger in the auroral regions, and that's shown in every model and almost every observation. Enter a new century, 2002, timed sounding of atmospheric using broadband emission radiometer instrument shows up on the scene. It's a limb viewing instrument that has most of its activity looking at that dark region of space where we can't see the emissions, but they're there. It has taken about 8.3 million radiance profiles per channel and it is still going, like the Energized Bunny. And even now, after 16 years, the noise levels are better than anything that can be measured at the ground if we're looking for the infrared signal. And so most of what I'm going to talk about from here on out, which is the results of the study that put me up here, it has to do with what is the time and space variability of nitric oxide and why does it do that? So one more from Marty Malinczak. What he's doing is taking the measured limb radiances, he's converting those into the cooling rate for nitric oxide, so no longer looking at the densities per se, but now its effect in cooling. He can vertically integrate that to give us kind of a global picture, and then over time he can see that that cooling, which is in the order of a few gigawatts compared to the sometimes thousands of gigawatts of heating that was coming in, has a solar cycle variation. And you go, well, wait a minute. If this is only a few gigawatts, what's happening to the rest? CO2 is taking care of that. But this is the highly variable, just-in-time cooling that you need for extreme storms. So, enter the work of undergraduates and graduates, students at CU, and I wanted to know a little bit more about what does the temporal variability look like? Not only just the spatial stuff, but and especially with respect to storms. So we started looking at isolated geomagnetic storms in the time frame 2010 to 2014. And the reason I wanted to do is I wanted to get away from any kinds of interference that might come from previous storms that had kind of riled up the atmosphere. So we did that first. What you see here, latitude on the vertical, time on the horizontal. This is a superposed epoch analysis where we've set our zero time to be something that we think is physically important. In this case, the zero time is the arrival of the coronal mass ejection that caused the storm. So we are looking at CMEs here. And if we look at sort of the median value displayed in this latitude time plot, what you can see is shortly after the arrival of the CME, we see the auroral regions light up and we see more nitric oxide emissions coming into lower latitudes. And you go, okay, that makes sense. We make it in the auroral zones. The wild heating that goes on generates gravity waves. The energy pulses out, and we end up with a little bit more nitric oxide cooling in kind of a global sense. If we look at the upper 75% of storms and beyond, you can see that there is a much larger reaction, but interestingly, there's a reaction or interaction going on ahead of these CME arrivals. And the question is, well, how does the system know that something's coming? Apparently it does. And the answer is that those storms, these very top 75% or more, are led by shock structures in the solar wind. So the fast CMEs are driving structures ahead of them that essentially also perturb the near-Earth space environment. And so the system gets a head start on the cooling. That is important. We'll step back and think about research to operations and operations to research. This whole study came about because the Air Force came to me in 2008 during efforts with the Multi-University Research Initiative program and said, we have some problem storms. Our DST method of just correlating with what the Disturbance Storm Time Index does And so when the disturbance storm time index goes down, we reduce the magnetic field at the equator due to the ring current. They had noticed that there was a really reproducible signature, meaning that the density at low Earth orbiting altitudes would go up, and it would slowly fade away in a nice, similar manner to which the DST index was fading away, except when it didn't. Okay, now that's a problem. You've got a forecasting method, but every now and then, it goes off track. And they wanted to know, why was it going off track? And I said, well, what's going on? What are the characteristics? And they go, we don't know. That's for you to figure out. So we spent 3.5 years figuring that out. And then over the course of probably 12 hours, the answer became very obvious. And it had to do with getting access to the SABRE data. So here is the summary of what we got out of looking at 11 of their so-called problem storms that they didn't know what was going on other than the forecasting method failed, and a similar number of storms within the same time frame between 2004 and 2008. And so we went back to basics, superposed epoch analysis. If you don't know what else to do, that's a great way to start. And we didn't know what else to do. One of the things that we noticed is that the problem storms in blue tended to have kind of a pulse of DST. So it indicated that the magnetosphere was becoming compressed. Something was causing the magnetosphere to get crushed. Maybe that has to do with shock arrival. Well, that's what I figured out later. And they tended to be somewhat stronger storms. But it was this part right here that we were most interested in. And what was going on in that 6 to 12 hours ahead was the CHIMP neutral density didn't seem to be going up commensurate with the fact that we were going to be in the midst of a pretty strong storm. So strong storm incoming, but neutral density not coming up to speed. And so what happened and what we found was that ultimately, when we went into the SABRE nitric oxide emission database, those storms that were behaving badly or oddly were those storms for which nitric oxide seemed to have gotten a running edge on and started cooling the system, or fighting, the cooling and the heating were actually competing. We extended this study because, that was just a couple dozen, so we extended the study in the space weather paper just mentioned, and we really went and said, hey, does it look like, is it the shocks, or is that what's going on? And you can tell here the SABRE nitric oxide flux for the shock events compared to the non-shock events, it's a very different profile. Those stronger storms are experiencing more nitric oxide cooling. We can also break it up by whether or not these events, these CMEs, are magnetic clouds or non-cloud ejecta. Very interestingly, the magnetic clouds are a much stronger, cause much stronger emission than do the non-cloud events. And you say, how could the atmosphere know if there's a magnetic cloud or not a magnetic cloud behind the shock? The atmosphere doesn't have any idea. Well, it does to a little bit of a degree, because magnetic clouds tend to be the ones that hit us nose on, and we actually see the smooth rotation. So when we're hit by the non-cloud ejecta, they don't have quite the same compressive characteristics, and so the atmosphere actually does know to some degree. It turns out that it's not only the cooling, but we need to be able to see this in the low Earth orbiting neutral density. And do we see a quick rise and then a sudden sharp drop in the neutral density, which is what we're expecting? And the answer is, yeah, we see that. So the nitric oxide is really kicked in during these energetic events. We wanted to know, well, what's causing this? And to some degree, you have to work with the tools that you have. We had a very long record of Defense Meteorological Satellite Program particle data. And so we started investigating the 1 to 10 keV electrons, the ones that have enough energy to rip apart the nitrogen molecules. And we see that during the shock magnetic cloud events, yep, that energy is up. If we look at the 10 keV ions, very interestingly, this is a slightly different path to make nitric oxide. They really ramp up just as we're transitioning from this shocked event in the solar wind into the CME. And this is just more that you can look at. We've investigated other parameters. We also see that the Joule heating comes up very rapidly in that 6 hours prior to CME arrival. We've looked at the distribution of the particles as they're coming into the auroral zone, north and south, magnetic clouds with shocks, those without. And what you see in that 24 hours prior to arrival is the auroral zone is lighting up with particle precipitation. And the same thing is true for the 10 to 30 keV ions. So how does this all fit together? And where do those coherent structures come in? So this is my cartoon that shows a CME with its turbulent sheath, so it's a fast CME that's driving a shock, approaching Earth. This turbulent sheath in here, you show it just wiggly field lines. It actually organizes the magnetic field that it is sweeping up or sweeping through into planar magnetic structures. And that has only recently become evident, but those planar magnetic structures means that we have several minutes to several hours of one orientation of interplanetary magnetic fields, some of which are going to be south. They also carry their own little density perturbations with them. And so our local friendly environment is being influenced by structures within structures of these fast CMEs. And what do? They create, when they pass, they create shock aurora, chorus waves, EMIC waves, all kinds of waves that alter the loss cone of particles for these particles and allow them to precipitate in. So here's just one example, best possible example. Here is the quiet before the storm. Here is the sheath region. Here is the CME. And what you see is the B is oscillating. Here are those planar field structures. And here are these density structures with 3 to 5 millihertz frequency, and they are influencing our system, rattling our system, so to speak. So this is what happens inside the magnetosphere. These solar wind density variations in the sheath are producing discrete global magnetospheric oscillations, chorus and EMIC wave enhancements that cause the precipitation of the particles. And if the IMF goes southward, which it inevitably will in these planar magnetic structures, then we get these pulses of enhanced Joule heating. Here's the details for those of you who want to read up on this. I will just point out to you this one at the bottom. And it's Nat Gopalswamy has noticed that for the magnetic clouds and the non-cloud ejecta, the magnetic clouds seem to represent that head-on CME structure that is going to give us the most compressive structure. So this is what we have, the particle precipitation, the Joule heating going into this region, really generating the nitric oxide. Is there real evidence for this? I list here a whole series of studies, some are about to be published, that show that yes, we get these extreme pulses of heating in the most extreme events, followed by a temperature crash that makes it very difficult to forecast for these extreme events what kind of thermosphere low Earth orbiting satellites are going to be going through. Is there a pattern? Corroborating evidence, it's always good to have somebody from completely outside of your team providing the backup. And so Eftahia Zesta and her postdoc, Denny Oliveira, are just on the verge of looking in detail at these events measured by CHAMP and seeing and GRACE and noticing exactly the same thing. The density recovery is typically 18 to 24 hours, except for those events where DST drops below minus 250, the extreme storms, and those are the ones where we get essentially the very rapid and unanticipated recovery. So the epilogue is that there are more studies than I can actually put in here. I will be writing an overview paper on this for some work that I'm doing under other funding, and so I'll be trying to capture this. But one of the things that I want to point out is that there are there's a talk here by Sheng Jing tomorrow afternoon about timed GUVI results, where he's talking about the meridional transport of NO during storm time. So how do we spread this out so that the whole globe is involved? And then my student Sierra Flynn has a poster where she has taken the 15 years worth of time SABRE data and has done the empirical orthogonal function analysis. I won't show you quite the piece de resistance, but here it is on the day side. We are seeing not only the auroral zone, but lots of emission on the day side that is a combination of transport and in-place creation by photoelectrons. And the more active regions that you have coming across the disk of the sun generating CMEs, the more extreme ultraviolet energy you're going to generate for this. So to conclude, these shock-led storms produce more NO emissions. The shock-led magnetic clouds tend to be the top producers. This is all part and parcel of this amazing molecule's ability to be a thermospheric thermostat. The fastest CMEs produce this condition where the nitric oxide generation is so great, or at least the emissions are so great, that the thermosphere is actually able to fight back and cool the atmosphere rapidly enough that we keep the lid on the system. There are specific events of this extreme overcooling. There are actually more than we know. Ryan McGranagan, my just graduated PhD student, has shown that this kind of thing is active even in the relative moderate interactions before the arrival of some high-speed streams. The only way that we're going to get the big picture view of this, I think, is to have full-on modeling efforts. This is a space weather issue in terms of satellite drag forecasting, and it is certainly worthy of a space weather system science endeavor. Thank you.